Hi, this is Julian from PopcornFX, and in this video I will show you how to shrink the particle size every time they collide with the scene. So to do that I will start with the tutorials package and I will use this effect, the sphere collisions effect. So this effect shows sphere sweeps with a non-zero collision radius, so this allows you to have spherical particles that collide with the proper radius in the scene instead of just a simple raycast. So the first thing I'll do is I'll reduce the spawn rate, and here in the layer the effect in the tutorials package uses a random radius, so I'll change that to have the same radius. I could just remove the random node, but just faster this way. So now we have big spheres bouncing around. And if I select the physics and scroll all the way down, you can see that in the outputs section there is a has collided Boolean output. So I will toggle that to make it visible. And I can use that with an if node, so that when it collides I take the radius and I shrink it down basically. So I can multiply the radius by, let's say, 0.5, so I'll divide it by 2 every time it collides, and the rest of the time for the frames where it does not collide, well, I will just take the radius unchanged. And here the result of that if will be the shrunk radius on the frames where collision happens and the unchanged radius when it doesn't happen. So if I just wire that to the scale of the mesh renderer node, you will see that it very briefly flashes on the frames where it collides. It's actually more visible if I lower the frame rate. But I want to remember that, obviously, from frame to frame. So to do that, I can insert a discretization point node. Unfortunately, it won't really do what I expect. So it will shrink for the first frame, but then it will stay at that size no matter how many times it bounces. And you will also see that the collision radius isn't right. It stays at whatever the original radius was. So this is because the discretization node here isn't able to go back through the if node to find where it should do the store. So we have to help it for that. So one way to do that is to use an assign node. So I take the initial spawn radius, and here if I use the assign node and wire in the if, I tell it to replace this value. However, it still doesn't work. It's even worse. Flashes one frame again and then goes back to the original size. Well, that's simply because this is a spawn value and we take the value at spawn here instead of taking the value from the previous frame. So what this does is just retake the 12 here, multiply it by 0.5, sorry, when it collides, and yeah, we just override it every time it collides without actually accumulating the shrunk value. So I could just set this pass-through to evolve, and it would extend the discretization path so that the wire here that we use to shrink is actually the wire from the start of the frame, so the value stored in the previous frame. And here it works. You see that this shrinks every time it collides, and however the collision radius obviously still uses the spawn value, so I can just rewire that. And now I have the expected behavior. I will just extend the lifetimes a bit. Right, so you see that now they do the expected thing. They shrink each time and they also update the collision radius. So as I mentioned in the first discretization video, I don't really like using pass-throughs at evolve, so instead I find it clearer to use another discretization node to determine, mark the beginning of the path. So that's basically it. You might be tempted to try rewiring some of this back into there. This will absolutely not work and will just break your effect. So yeah, you don't have another choice than using discretization here. And you can't also control G that, because it will also create a loop in the graph, and somehow it appears to work for the scale, but you'll see that the part that loops, which is the one going back into the collision radius, actually doesn't work, because here it's as if we had a collision radius of 0. So now the balls are penetrating the ground. So yeah, you have to keep this in there. You can control G part of it to clean up your graph, but this is one of the cases where you will have to have such a path in your actual simulation graph, at the root of your simulation graph. That's it for this video. Hope you enjoyed it and found it useful. See you next time.